Modern air combat is no longer decided by who turns the tightest corner or climbs the fastest into the sky. Those measures once defined air superiority, but today, they tell only a small part of the story. In the 21st century, air combat is shaped by something far less visible: information. Who sees first? Who understands the environment faster? And who connects more systems together into a single, coherent picture of the battlefield? Two of the most advanced fighter aircraft ever developed, the American F-35 Lightning II and the Russian Su-57 Felon, represent two very different approaches to this new reality. On the surface, both are fifth-generation fighters. Both are designed to operate in highly contested environments. And both reflect the strategic priorities of the nations that built them. But beneath their external appearance lies a deeper difference in philosophy. This video is not about dogfights in the clouds. It's not about dramatic close-range maneuvers. And it's not about declaring one aircraft better than the other. Instead, this is a systems-level story. It's about how modern sensors, data fusion, networking, and decision-making can shape an engagement long before two aircraft ever come within visual range. In today's environment, an aircraft may already be detected, tracked, and evaluated without knowing it. The F-35 was designed around this idea from the very beginning. Rather than acting alone, it functions as part of a larger network, collecting information, sharing it, and quietly influencing the battle space. The aircraft's role is not just to fly or fight, but to see, interpret, and connect. The Su-57 follows a different design path, blending advanced features with more traditional performance priorities. Understanding the contrast between these approaches reveals how modern air power has evolved and where it may be headed next. By the end of this video, you'll understand how the F-35 is designed to operate in ways that may allow it to avoid early detection, manage when and how it is seen, and shape the environment around it, often without ever being visually observed by an opposing aircraft. This is the story of modern air combat, where the most important battles are fought before anyone realizes they've begun. Wars are won by systems, not planes. For much of aviation history, air combat was defined by what could be seen with the naked eye. Pilots searched the sky for movement. Victory often went to whoever could climb higher, turn tighter, or accelerate faster. Aircraft were judged by visible performance, speed, agility, and raw power. Even today, when people compare fighter jets, these are often the first metrics discussed. Top speed, thrust-to-weight ratio, maneuverability at high angles of attack. These characteristics still matter, but they come from an earlier era of air warfare, one shaped by close-range encounters and limited situational awareness. Modern air combat operates under a very different set of assumptions. In today's environment, the decisive factors are often invisible. They exist not in the shape of the aircraft, but in the flow of information surrounding it. Rather than being defined by individual performance, modern air power is defined by systems, interconnected networks of sensors, data processors, and decision-making tools that extend far beyond any single aircraft. At the center of this shift are three foundational elements: information, networking, and decision speed. Information is the raw material of modern warfare. It includes radar data, infrared signatures, electronic emissions, satellite feeds, and signals intelligence. But information alone has limited value unless it can be interpreted quickly and accurately. Networking determines how that information moves. It allows data collected by one platform to be shared instantly with many others. A radar contact detected hundreds of miles away can become relevant to an aircraft that never turned its own sensors on. Decision speed is the final element. It is not just about how fast a pilot reacts, but how quickly a system can process information, prioritize threats, and present clear options. In modern combat, seconds can matter, but only if those seconds are used effectively. These three elements form the foundation of contemporary air warfare. This is where the design philosophies of the F-35 Lightning II and the Su-57 Felon begin to diverge in meaningful ways. The F-35 was conceived during a period when military planners were already thinking beyond traditional air-to-air combat. Rather than being built as a standalone fighter that excels primarily through flight performance, the F-35 was designed from the beginning as a sensor platform, an aircraft whose primary role is to collect, process, and distribute information. In this philosophy, the aircraft itself is only one component of a much larger system. Every aspect of the F-35's design reflects this approach. Its sensors are not treated as separate tools, but as inputs into a unified picture. Radar, infrared systems, electronic surveillance, and external data sources are fused together automatically. The pilot does not manually interpret raw data streams; instead, the aircraft presents an integrated understanding of the battlespace. This changes the role of the pilot fundamentally. Rather than acting primarily as a sensor operator, the pilot becomes a decision-maker evaluating options based on a comprehensive, continuously updated picture. The Su-57, by contrast, reflects a different design balance. It incorporates modern sensors and reduced observability features, but it also places significant emphasis on traditional performance characteristics such as speed, agility, and kinematic capability. This approach aligns with a long-standing focus on aerodynamic performance and high-energy maneuvering. Neither philosophy is inherently right or wrong. They are responses to different strategic priorities, industrial capabilities, and historical experiences. But they lead to very different assumptions about how air combat unfolds. In earlier generations of aircraft, the pilot's situational awareness was limited by what their own sensors could detect. Radar coverage was narrower. Information sharing was slower. Each aircraft operated largely as an independent entity. Modern platforms operate differently. The F-35 does not rely solely on what it can see with its own sensors. It is designed to operate as part of a distributed combat system. Information flows continuously between aircraft, ships, ground-based radars, satellites, and uncrewed platforms. Data collected by one node in the network becomes available to many others almost instantly. This means the aircraft does not need to expose itself to gather information. It can receive targeting data from other platforms while maintaining a lower observable profile. In practical terms, this allows the F-35 to remain aware of its environment without announcing its presence through active emissions. This concept represents a significant shift in air warfare philosophy. Instead of asking, "What can my aircraft do on its own?" the question becomes, "How does my aircraft contribute to the larger system?" In this environment, individual performance metrics become less decisive. A faster aircraft does not automatically gain an advantage if it lacks accurate information. A highly maneuverable platform may never have the opportunity to use that maneuverability if it is detected, tracked, and managed at long range. Control of information becomes control of the engagement. This does not mean that aircraft no longer fight. It means that many of the most important decisions are made before traditional combat parameters come into play. Distance, altitude, timing, and positioning are influenced long before opposing aircraft ever approach each other. Military analysts often describe this as shaping the battlespace. Battlespace shaping involves influencing the conditions of an engagement in advance, determining when contact occurs, under what circumstances, and with which advantages. In modern air combat, the aircraft that controls information can influence these variables without ever revealing itself. The F-35's design reflects this priority. Its ability to gather information passively, integrate data from multiple sources, and share the data across a network allows it to function as both a sensor and a coordinator. It contributes to a collective understanding that no single platform could achieve alone. The Su-57, operating under a different doctrinal framework, emphasizes flexibility and performance within its own capabilities. Its design suggests an expectation that aircraft may need to rely more heavily on their individual characteristics in contested environments. Again, these are not value judgments, they are reflections of different strategic assumptions. One approach prioritizes integration and network dominance. The other balances modern features with traditional air combat strengths. Understanding these philosophies helps explain why comparisons based solely on speed or maneuverability often miss the larger picture. In modern air warfare, superiority is increasingly defined by who knows more, sooner, and more accurately. The aircraft that can build a clearer picture of the environment and share it effectively can influence events without escalating them. It can deter, observe, or position itself advantageously without forcing a confrontation. This is why modern air forces invest heavily in connectivity, data fusion, and decision support systems. The aircraft itself becomes less important than the ecosystem it operates within. The F-35 was built to thrive in this ecosystem. Its strength lies not in any single attribute, but in how its systems work together seamlessly. It is designed to reduce uncertainty for its operators and for the network it supports. As we move deeper into the era of fifth-generation warfare, this philosophy continues to shape how aircraft are designed, deployed, and evaluated. Air combat is no longer a contest between isolated machines, but a competition between systems of systems. This chapter lays the foundation for everything that follows. To understand how one aircraft might influence an engagement without being seen, we must first understand why seeing first matters and why, in modern warfare, the most decisive battles are often fought in the realm of information long before weapons are ever discussed. Low observability is about consistency, not invisibility. Stealth is one of the most discussed and most misunderstood concepts in modern air combat. Popular culture often portrays stealth aircraft as being invisible, able to move freely through defended airspace without ever being detected. In reality, stealth does not mean absence. It means management of signatures, emissions, and expectations. At its core, stealth is about reducing detection range and delaying identification. It seeks to limit how far away an aircraft can be detected, how confidently it can be tracked, and how quickly it can be classified. Even small reductions in detection range can have significant effects on how an engagement unfolds. This is why modern stealth must be understood not as a single feature, but as a system, one that works only when multiple elements function together consistently. The most visible aspect of stealth is aircraft shape. Faceted surfaces, aligned edges, and carefully angled inlets are all designed to reduce how radar energy reflects back to its source. But shape alone is only the starting point. The F-35's low observability extends far beyond its external geometry. Its surfaces are coated with radar-absorbent materials designed to reduce reflected energy across specific frequency bands. These materials are not decorative, they are engineered components that must be maintained precisely to preserve performance. Another critical element is internal weapon carriage. External stores, weapons, fuel tanks, pods create hard edges and reflective surfaces that dramatically increase radar signature. By carrying its primary mission equipment internally, the F-35 maintains a cleaner, more predictable radar profile. Equally important is emissions management. Radar is not the only way an aircraft can be detected. Heat, radio frequency transmissions, and electronic signals all contribute to an aircraft's observability. The F-35 is designed to manage these emissions carefully, allowing it to collect information without continuously advertising its presence. Thermal signatures, for example, are influenced by engine placement, exhaust design, and heat dissipation. While no jet aircraft can eliminate heat output, managing how that heat is distributed and exposed can reduce detection by infrared sensors. Perhaps one of the least discussed yet most important aspects of stealth is consistency. An aircraft's radar cross-section is not a single number. It changes based on angle, configuration, and operating conditions. A stealth aircraft is designed to minimize these fluctuations, maintaining a relatively predictable signature across a wide range of viewing angles. This predictability matters because it creates uncertainty for opposing sensors. If detection occurs later, less confidently, or intermittently, it becomes more difficult to track, classify, and respond effectively. The F-35 was designed with the systems-level approach in mind. Its stealth features are integrated across structure, materials, sensors, and software. Each element reinforces the others, creating a more consistent low-observable profile. The Su-57 also incorporates stealth principles, but it follows a different design balance. Its airframe includes shaping intended to reduce radar signature, as well as internal weapon bays and advanced materials. However, it also emphasizes high-speed performance, agility, and aerodynamic flexibility. These priorities introduce trade-offs. Designing for extreme maneuverability and speed often requires features such as movable surfaces, exposed engine components, or certain intake geometries that can complicate signature management. This does not mean one approach is ineffective, it means the balance between observability and performance is different. In practical terms, this can result in non-symmetrical detection. One aircraft may detect the other at a different range, under different conditions, and with varying confidence. Detection is not a simple on or off switch, it is a probabilistic process influenced by environment, sensor type, and aircraft behavior. This is why stealth cannot be evaluated in isolation. Environmental factors such as terrain, weather, altitude, and electromagnetic clutter all affect detection. So do the capabilities and limitations of the sensors involved. A design optimized for certain conditions may perform differently in others. What matters operationally is not absolute invisibility, but time. If one aircraft can delay detection even by seconds or minutes, the time can be used to gather information, reposition, or shape the engagement environment. This is often referred to as decision advantage. The aircraft that is detected later has more control over when and how interactions occur. It can observe without being observed, or disengage without escalating. In many cases, it can influence outcomes without ever being visually seen. This concept reshapes how air combat is understood. In earlier eras, the first visual contact often triggered the beginning of an engagement. Today, detection may occur electronically long before pilots are aware of each other. The aircraft that manages its signatures more effectively can operate with greater freedom within this invisible battlespace. The F-35's stealth philosophy aligns closely with this reality. Its design seeks to reduce not just peak visibility, but variability, creating a stable, manageable signature that integrates with its sensor and networking advantages. The Su-57's design reflects a different expectation of how engagements may unfold, balancing reduced observability with the ability to perform across a wide range of flight regimes. Neither approach guarantees outcomes. Stealth is not a shield, and detection does not equal defeat. What stealth offers is options to observe, to decide, and to act on favorable terms. Understanding stealth as a system rather than a shape helps explain why comparisons based on visual appearance alone can be misleading. The most important elements of low observability are often invisible, embedded in materials, software, and operational concepts. As we move deeper into the era of fifth-generation warfare, stealth continues to evolve. It is no longer a singular advantage, but one component of a broader strategy focused on uncertainty, information dominance, and decision speed. In the next chapter, we will explore how sensors and data fusion transform these stealth advantages into actionable understanding, and why, in modern air combat, seeing clearly matters just as much as being seen late. The pilot sees a single picture, not multiple screens. One of the most significant changes in modern air combat has nothing to do with speed, altitude, or maneuverability. It has to do with how information is presented to the pilot. For decades, fighter pilots operated as interpreters. Radar screens, infrared displays, electronic warning indicators, and radio communications all competed for attention. Pilots were trained not just to fly the aircraft, but to mentally assemble fragments of information into a coherent understanding of the situation around them. This process required skill, experience, and constant attention. It also placed enormous cognitive demands on the pilot, especially in high-stress environments where decisions needed to be made quickly and accurately. As aircraft became more capable, the volume of information increased. Sensors became more powerful, data streams more complex, and operational environments more crowded. At a certain point, simply adding better sensors no longer solved the problem. The challenge shifted from collecting information to making sense of it. This is where sensor fusion becomes transformative. Sensor fusion is not just about displaying more data. It is about combining multiple sources of information into a single, integrated picture that reflects what is most relevant to the pilot at any given moment. The F-35 was designed with this concept at its core. Instead of treating radar, infrared, electronic support measures, and external data feeds as separate inputs, the aircraft's systems merge them automatically. The result is a unified representation of the battlespace, continuously updated and prioritized. In practical terms, this means the pilot does not see multiple screens competing for attention. They see one picture, a synthesized understanding of their environment. Contacts are automatically correlated across sensors. If one system detects a signal and another confirms it, the aircraft associates those inputs into a single track. The system evaluates confidence levels, classifies contacts, and presents the information in a way that supports decision-making rather than interpretation. This fundamentally changes the pilot's role. Instead of spending time analyzing raw data, the pilot can focus on managing the situation. Decisions become less about deciphering what might be happening and more about choosing how to respond. Reducing pilot workload is not a matter of convenience. It is a matter of performance and safety. High cognitive load increases the risk of error, delays reaction time, and limits the ability to adapt to unexpected changes. By automating data integration and prioritization, sensor fusion helps ensure that critical information is not lost in noise. The system highlights what matters most, allowing the pilot to maintain situational awareness even in complex environments. This approach reflects a broader trend in modern military systems: human-machine teaming. Rather than replacing the human operator, advanced systems are designed to support them, handling repetitive or data-intensive tasks so humans can focus on judgment and strategy. The Su-57 also integrates advanced sensors, including infrared search and track systems designed to detect aircraft without relying on radar emissions. These capabilities enhance situational awareness and reduce dependence on active sensors. However, the level of automation and integration differs. The way information is presented, correlated, and prioritized reflects different design philosophies and operational assumptions. Some approaches place greater emphasis on pilot interpretation, allowing experienced operators to manually assess sensor data. Others prioritize automation, aiming to reduce cognitive load and standardize decision-making across a wide range of scenarios. Neither approach is inherently superior in all contexts. The effectiveness of sensor fusion depends on reliability, training, and trust. Pilots must understand how the system works, what its limitations are, and when to rely on their own judgment. In modern air combat, the pace of events makes this balance increasingly important. Engagements unfold across vast distances, with multiple actors influencing the environment simultaneously. Information arrives from sources that may be far removed from the aircraft itself: satellites, ground stations, other aircraft, and uncrewed systems. Without effective fusion, this flood of data can overwhelm even the most skilled operator. With effective fusion, it becomes a source of advantage. Information dominance is not about knowing everything. It is about knowing what matters, sooner and more clearly than others. The aircraft that can achieve this gains the ability to shape events rather than react to them. This advantage does not require direct confrontation. An aircraft that understands the environment better can choose when to engage, when to observe, and when to avoid unnecessary risk. It can position itself more effectively and coordinate with other platforms more efficiently. In this sense, sensor fusion contributes to control of the battlespace without ever firing a shot. It is also important to recognize that sensor fusion is not static. It evolves through software updates, algorithm improvements, and integration with new platforms. The aircraft becomes a platform for continuous improvement rather than a fixed set of capabilities. The F-35's emphasis on software-driven fusion reflects this adaptability. As new sensors and data sources become available, they can be incorporated into the system, expanding the aircraft's understanding of its environment. This adaptability contrasts with earlier generations of aircraft, where upgrades often required physical modifications and lengthy integration processes. In environments where threats and technologies evolve rapidly, the ability to update how information is processed can be as important as hardware performance. Ultimately, sensor fusion changes the nature of air combat by shifting the focus from mechanical skill to cognitive advantage. The aircraft that can present its pilot with a clearer, more accurate picture of the battlespace enables faster, more confident decisions. Over time, this consistency can shape outcomes even in the absence of direct engagement. This is why modern air forces place such emphasis on information systems, training, and integration. The goal is not just to build faster aircraft, but to create platforms that help humans operate effectively in increasingly complex environments. In the next chapter, we will explore how these fused sensor capabilities extend beyond the aircraft itself, connecting multiple platforms into a network system that sees farther, responds faster, and operates as a unified whole. Because in modern air warfare, information is only powerful when it is shared. You don't need to see the target to know where it is. Perhaps the most important advantage of modern combat aircraft is not what they can see with their own sensors, but what others can see for them. For much of aviation history, an aircraft's awareness of its environment was limited by its own instruments. Radar range, line of sight, and pilot perception defined what was possible. Each aircraft functioned largely as an independent observer, responsible for detecting, identifying, and responding to threats on its own. That model no longer defines modern air warfare. Today, air combat takes place within a vast, interconnected information environment. Sensors are distributed across air, sea, space, and land. Data flows continuously between platforms, often far beyond visual or radar range. In this environment, the aircraft itself becomes only one element within a much larger system. This is the foundation of networked warfare. Rather than relying solely on onboard sensors, modern platforms are designed to receive, process, and act upon information collected elsewhere. This allows them to operate with a level of awareness that would be impossible to achieve independently. The F-35 was built specifically for this environment. From its earliest design stages, it was intended to function as a networked node, a participant in a broader information ecosystem rather than a self-contained unit. This ecosystem includes a wide range of off-board sensors. Airborne Early Warning and Control aircraft, often referred to as AWACS, provide long-range radar coverage that extends far beyond the horizon of individual fighters. Naval radar systems contribute additional detection capability from the sea. Satellites offer persistent surveillance and global context. Other fighters share localized observations. Uncrewed platforms add flexibility and reach without risking human operators. Each of these systems collects information from a different vantage point, using different sensor types, and under different conditions. Individually, their perspectives are limited. Collectively, they form a far more complete picture. The F-35's role within this network is not simply to receive data, but to integrate it seamlessly with its own sensor inputs. Information arriving from off-board sources is fused automatically, correlated with on-board observations, and presented as part of a unified battlespace picture. This integration allows the aircraft to maintain high situational awareness while managing its own emissions carefully. Operating sensors actively, especially radar, can reveal an aircraft's presence. In a networked environment, however, an aircraft does not always need to rely on its own emissions to understand what is happening around it. By receiving data from other platforms, it can reduce the need to transmit signals that might increase detectability. This capability reflects a broader shift in how air combat is conducted. Rather than two aircraft approaching each other independently, engagements increasingly involve interacting networks. Information moves faster than aircraft. Decisions are shaped by data that may originate hundreds or even thousands of miles away. In this context, the aircraft becomes a node, not the center. A node contributes to the network by collecting information, sharing it, and acting on what the network provides. Its value lies not only in its individual performance, but in how effectively it supports and benefits from the collective system. This changes how advantages are measured. In earlier eras, superiority was often associated with individual aircraft characteristics, speed, climb rate, or weapon capacity. In a networked environment, superiority is increasingly associated with connectivity, resilience, and integration. An aircraft that can see farther through the network, understand the situation more clearly, and coordinate more effectively with others gains an advantage that is difficult to counter through individual performance alone. The F-35's networking capabilities reflect this philosophy. It is designed to share information with other F-35s, with legacy aircraft, and with surface and space-based systems. Data links allow information to flow in multiple directions, creating a shared understanding across different platforms and domains. This shared understanding reduces uncertainty. When multiple sensors observe the same event from different angles, confidence increases. Ambiguity decreases. Decisions can be made with greater assurance. The Su-57 also operates within a networked environment and is intended to integrate with other platforms. However, the scope, maturity, and emphasis of these networks reflect different strategic priorities and technological ecosystems. The effectiveness of networked warfare depends not only on individual aircraft, but on the broader infrastructure that supports them: communication systems, data processing capabilities, and organizational doctrine. This highlights an important reality: modern air combat cannot be separated from the systems that surround it. An aircraft operating within a robust, resilient network can achieve levels of awareness and coordination that far exceed what it could accomplish alone. Conversely, disruptions to that network can reduce effectiveness even if the aircraft itself remains capable. As a result, modern military planning places significant emphasis on protecting information flows, ensuring redundancy, and maintaining connectivity in contested environments. Networked warfare also changes how engagements begin and end. Instead of sudden encounters between isolated aircraft, interactions may be shaped gradually through information exchange. Presence can be monitored. Movements can be anticipated. Responses can be calibrated without immediate escalation. This allows for greater control over timing and intensity. An aircraft that understands the broader context can choose when to reveal itself, when to remain passive, and when to reposition. It can coordinate with others to manage space and influence outcomes without forcing direct confrontation. This does not eliminate conflict, but it introduces new ways of managing it. In this environment, the traditional image of air combat, two jets meeting unexpectedly and reacting in the moment, becomes less representative of reality. The decisive moments often occur earlier, in the invisible realm of data and decision-making. The F-35's design reflects an understanding of this shift. Its strength lies not only in what it can do independently, but in how it functions as part of a larger system that spans multiple domains. By operating as a node within a network, the aircraft contributes to and benefits from a collective advantage. Information gathered by one platform enhances the effectiveness of others. Decisions made by one node influence the behavior of the entire system. This interconnectedness defines modern air warfare. Understanding networked warfare and offboard sensors is essential to understanding how one aircraft might influence an engagement without being seen. It is not about secrecy alone, it is about context, about knowing where you fit within a complex, dynamic environment. In the next chapter, we will explore how this networked awareness translates into decision advantage and seconds matter more than speed. Modern air engagements do not unfold the way they once did. Gone are the days when two aircraft unexpectedly encountered each other at close range and relied purely on reflexes, maneuverability, and raw performance. Today's engagements are shaped long before aircraft ever come near one another, often without either side realizing a contest has begun. The defining feature of this new environment is compressed time. Advances in sensors, networking, and information processing mean that detection, identification, and assessment happen faster than ever before. What once took minutes can now take seconds. As a result, the margin for hesitation has narrowed dramatically. In this environment, the advantage often belongs to the platform that can do three things consistently: identify potential threats earlier, classify them faster, choose from more options. These capabilities do not guarantee a specific outcome. Air combat is inherently uncertain, shaped by human decisions, environmental conditions, and countless variables. But they do something just as important: they shape the engagement space. Shaping the engagement space means influencing the conditions under which interactions occur. It means controlling distance, timing, and positioning before a situation escalates into direct confrontation. This is what military analysts refer to as battle space control. At its core, battle space control is about choice. An aircraft that understands the environment earlier has more choices available. It can observe without engaging. It can reposition quietly. It can coordinate with others. It can disengage entirely. Each additional second of awareness expands the set of possible actions. Speed, in the traditional sense, still matters. But speed alone does not create advantage if it is not paired with information and decision-making. A faster aircraft that reacts late may still find itself constrained. A slower aircraft that reacts early may shape the encounter in its favor. This inversion of priorities is one of the most important shifts in modern air warfare. Decision time begins with detection. Detection does not mean immediate clarity. Initial observations are often uncertain, faint signals, partial tracks, or ambiguous data. The challenge is not simply noticing something, but determining what it is and what it represents. This is where classification becomes critical. Classification involves correlating data from multiple sources, evaluating confidence, and assigning meaning. Is the contact airborne or ground-based? Is it moving in a predictable pattern? Does it match known profiles? Each answer refines understanding and reduces uncertainty. The faster this process occurs, the sooner meaningful decisions can be made. Modern platforms are designed to accelerate this cycle. Automated systems correlate sensor inputs, compare them against known patterns, and present prioritized assessments to the pilot. The goal is not to remove human judgment, but to ensure that judgment is informed and timely. Once a situation is understood, options become available. Options may include maintaining distance, changing altitude, altering course, coordinating with other platforms, or simply continuing to observe. The presence of options is itself a form of advantage. An aircraft with limited awareness may be forced into reactive behavior. An aircraft with greater awareness can behave deliberately. This distinction is central to battle space control. By managing when and how it is detected, an aircraft can influence the geometry of an engagement. Distance determines how much time is available to react. Altitude affects sensor performance, fuel efficiency, and maneuver options. Timing influences coordination with other assets and environmental factors. Control over these variables does not require confrontation. It requires anticipation. The F-35's design emphasizes this anticipatory approach. Its ability to operate with reduced observability, fused sensors, and networked awareness allows it to perceive the battlespace earlier and more clearly. This clarity translates into time, and time translates into control. This control is subtle. It is not about dramatic maneuvers or visible dominance. It is about quiet influence. An aircraft that is detected later can choose how to respond to detection. It can reposition before being fully tracked. It can manage distance to maintain flexibility. It can align itself with favorable conditions without drawing attention. In many cases, this influence may never be visible to an observer. The outcome may appear uneventful: no close encounter, no escalation, no obvious exchange. Yet the battlespace has been shaped nonetheless. This is an important point. Battlespace control does not always produce spectacle. Often, its success is measured by what doesn't happen. The absence of surprise, the avoidance of unfavorable positioning, and the maintenance of strategic flexibility are all indicators of effective control. This perspective helps explain why modern air forces place such emphasis on early warning, data integration, and decision support. The goal is not simply to react faster, but to act earlier. Acting earlier means operating before constraints narrow. It means shaping conditions rather than responding to them. The Su-57, like other advanced platforms, operates within this same temporal environment. Its design reflects an understanding that decision speed and situational awareness are critical. However, the specific balance between automation, pilot interpretation, and system integration differs. Different design choices lead to different strengths and limitations. Some approaches emphasize pilot-driven adaptability. Others emphasize system-driven consistency. Each reflects assumptions about training, doctrine, and operational context. What matters in this chapter is not comparison for its own sake, but understanding the underlying principle: time is the most valuable resource in modern air combat. Time allows for coordination. It allows for verification. It allows for restraint. And when necessary, it allows for decisive action. Battlespace control is the art of preserving time for yourself while limiting it for others. This concept applies beyond individual aircraft. Networks of platforms work together to extend awareness and compress decision cycles. Information shared early allows multiple actors to align their actions without delay. This collective decision advantage compounds. Each node that understands the environment earlier contributes to the system's overall effectiveness. The result is not just faster reactions, but more coherent ones. In this environment, the traditional emphasis on raw performance metrics becomes less predictive of outcomes. Speed, agility, and power matter, but they are contextualized within a broader framework of information and timing. An aircraft that excels in performance but lacks early awareness may find itself constrained. An aircraft that excels in awareness may avoid situations where performance limits are tested at all. This does not mean that air combat has become deterministic or predictable. Uncertainty remains. Human judgment remains central. Environmental factors still matter. What has changed is where advantage begins. Advantage now begins with perception, not proximity. It begins with understanding, not encounter. It begins with decision time. By identifying potential threats earlier, classifying them faster, and choosing from more options, modern platforms can influence engagements before they fully materialize. This influence defines battlespace control. As we approach the final chapter, this concept becomes crucial. Understanding how time and decision shape the environment helps explain why some aircraft are designed to avoid being seen, not for concealment alone, but to preserve the freedom to choose. Because in modern air warfare, the most decisive moments often occur before anyone realizes a fight was possible at all. Technology reflects doctrine. Comparisons between advanced military aircraft often generate strong reactions. Speed, stealth, maneuverability, and technology are weighed against each other in search of a definitive answer. But when it comes to platforms like the F-35 Lightning II and the Su-57 Felon, simple comparisons miss the deeper story. These aircraft are not direct mirrors of each other. They were conceived in different strategic environments, built by different industrial ecosystems, and shaped by different military doctrines. Each reflects the priorities, assumptions, and constraints of the nation that developed it. Understanding what this comparison really means requires stepping back from the aircraft themselves and looking at the ideas behind them. The F-35 emerged from a strategic context that prioritized coalition operations, global reach, and information integration. It was designed to operate alongside a wide range of platforms, from legacy aircraft to naval and space-based systems, across multiple domains. This emphasis on integration is not accidental. Modern military operations increasingly involve joint and combined forces. Aircraft must communicate effectively with ships, ground units, satellites, and allied platforms. The ability to share information quickly and securely becomes a central requirement. As a result, the F-35 was built around information dominance. Its value lies not only in what it can do on its own, but in how it contributes to a shared understanding of the battle space. Sensors, data fusion, and networking are treated as primary capabilities, not supporting features. The Su-57 reflects a different strategic emphasis. Its design suggests a focus on flexibility within national systems, high-performance flight characteristics, and the ability to operate in environments where access to broad networks may be limited or contested. This reflects different assumptions about how conflicts may unfold and what capabilities will be most reliable. These differences highlight an important truth: military technology does not exist in isolation. It is shaped by doctrine, by how nations expect to use force, deter adversaries, and protect their interests. Doctrine influences design choices. A doctrine that emphasizes joint operations and global connectivity will prioritize interoperability, data sharing, and standardized systems. A doctrine that emphasizes autonomy and performance may prioritize agility, speed, and self-contained capability. Neither approach is universally superior. Each is optimized for different scenarios and strategic goals. This is why declaring a winner based on isolated characteristics is misleading. Air superiority in the 21st century is not a single attribute. It is an emergent property of how multiple capabilities interact. Information dominance, networking, low observability, and decision speed are not independent factors. They reinforce each other. Low observability extends the time available to gather information. Networking expands the scope of that information. Sensor fusion turns data into understanding. Decision speed converts understanding into action. Together, these elements redefine what air superiority looks like. Instead of focusing on individual encounters, modern air power focuses on control of information, control of timing, and control of escalation. The ability to shape conditions without forcing confrontation becomes a form of power in itself. This shift has implications beyond aircraft design. It influences training, command structures, and even how nations think about deterrence. A system that can observe, coordinate, and respond quickly may deter conflict simply by reducing uncertainty and increasing predictability. In this sense, platforms like the F-35 are not just tools of combat. They are tools of influence. They signal technological capability, organizational sophistication, and strategic intent. Their presence can reassure allies, complicate adversary planning, and shape regional dynamics without direct engagement. The Su-57 plays a similar role within its own strategic context. It represents technological ambition, industrial capability, and a commitment to maintaining advanced air power. Its design reflects confidence in traditional performance metrics alongside modern enhancements. Understanding these platforms as expressions of national strategy helps explain why comparisons often generate more heat than light. They are not just machines, they are symbols of how different societies approach security and power. Looking forward, the future of air combat is likely to amplify these trends rather than reverse them. Emerging technologies such as artificial intelligence, advanced uncrewed systems, and resilient communications networks will further emphasize system-level performance. Individual aircraft will matter, but primarily as components of larger, adaptive ecosystems. Human operators will remain central, but their role will continue to evolve. Decision-making will increasingly involve collaboration between humans and machines, supported by systems that manage complexity and reduce cognitive burden. In this future, success will depend less on isolated excellence and more on coherence, how well systems work together across domains and organizations. This does not mean that traditional attributes like speed and maneuverability will disappear. They will remain relevant, but they will be contextualized within a broader framework of information and integration. The comparison between the F-35 and the Su-57, then, is not about which aircraft would prevail in a hypothetical encounter. It is about what each aircraft reveals about the direction of modern military thought. It shows how different nations prioritize information, connectivity, and autonomy. It highlights the trade-offs inherent in designing for complex, uncertain environments. Most importantly, it reminds us that technology is a reflection of human choices. Every design decision embodies assumptions about threats, opportunities, and values. By studying platforms like the F-35 and the Su-57, we gain insight not only into engineering, but into strategy itself. Air superiority in the 21st century is no longer defined by dominance in the sky alone. It is defined by the ability to understand, decide, and coordinate across vast, interconnected systems. That is what this comparison really means. And as technology continues to evolve, the aircraft that matter most may not be the ones that fly the fastest or turn the hardest, but the ones that help nations think, connect, and act more effectively in an increasingly complex world. The next advantage won't belong to aircraft, but to adaptability. As advanced as today's fifth-generation fighters are, one of the most important lessons from comparing platforms like the F-35 and the Su-57 is this: they are not the end of the story. They are transitional systems, bridges between the age of standalone aircraft and an era defined by adaptability, autonomy, and constant evolution. Modern air combat is no longer static. The pace of technological change has accelerated to the point where no single design can remain dominant indefinitely. Sensors improve. Networks expand. Countermeasures evolve. Software updates can alter capabilities faster than new aircraft can be built. In this environment, the most important question is no longer, which aircraft is better? It becomes, which system can adapt faster? This shift fundamentally changes how air power is evaluated. In earlier eras, air superiority could be measured by production numbers, engine performance, or weapon range. Those metrics still matter, but they no longer tell the full story. Today, effectiveness depends on how quickly a system can absorb new information, integrate new technologies, and adjust to unexpected conditions. Adaptability becomes a strategic asset. The F-35 was designed with this principle in mind. Its heavy reliance on software, sensor fusion, and networking allows its capabilities to evolve without redesigning the airframe. New sensors, data sources, and processing techniques can be integrated over time, expanding what the aircraft can understand and share. This approach treats the aircraft less as a finished product and more as a platform for continuous development. The Su-57, operating within a different industrial and strategic context, reflects another approach emphasizing performance and flexibility within the aircraft itself. This highlights a broader tension in modern military design: how much capability should be embedded in hardware, and how much should be delivered through software and networks. Neither approach is inherently future-proof. As systems become more interconnected, they also become more complex. Complexity introduces vulnerabilities, not just technical, but organizational. Maintaining coherence across networks, platforms, and operators becomes a challenge in itself. This is where doctrine and training play a decisive role. Advanced technology cannot compensate for poor integration or unclear decision-making. The effectiveness of future air combat systems will depend as much on how people use them as on what they can technically do. Another major factor shaping the future of air combat is the rise of uncrewed and semi-autonomous systems. Rather than replacing piloted aircraft, these systems are increasingly designed to complement them. Uncrewed platforms can extend sensor reach, operate in high-risk environments, and provide additional perspectives to the network. In this model, the piloted aircraft becomes a command and coordination hub, a decision-making node rather than a lone actor. This further reinforces the idea that air combat is becoming a contest between systems of systems, not individual machines. As these technologies mature, comparisons between single aircraft will become even less meaningful. Future engagements may involve dozens of interconnected platforms, each contributing partial information and limited actions. The outcome will depend on how well these elements synchronize, how effectively they share information, allocate tasks, and adapt to disruption. This raises an important point: resilience. In a highly networked environment, disruption is inevitable. Communications may be degraded. Sensors may be denied. Systems may fail or provide conflicting data. The advantage will belong to systems that can continue operating under imperfect conditions. Resilience is not about perfection. It is about maintaining usefulness despite uncertainty. This is why modern air forces invest heavily in redundancy, training, and decentralized decision-making. The goal is not to eliminate friction, but to function effectively within it. When viewed through this lens, the comparison between the F-35 and the Su-57 becomes less about performance metrics and more about strategic intent. Each aircraft represents a different answer to the same underlying question. How do you maintain air power in a world where information moves faster than aircraft? The answer is not static. It will continue to evolve as technology, doctrine, and geopolitics change. What remains constant is the importance of understanding context. No aircraft operates in isolation. Geography, alliances, industrial capacity, and organizational culture all shape how technology is used. An aircraft optimized for one strategic environment may be less effective in another, not because it is inferior, but because its assumptions do not align with reality. This is why simplistic comparisons often fail. They strip away context and focus on isolated attributes, ignoring the systems and decisions that give those attributes meaning. In doing so, they miss the most important lesson of modern air warfare: capability emerges from integration. Looking ahead, future air combat will likely emphasize faster decision cycles, greater human-machine collaboration, increased reliance on distributed sensors, continuous software-driven evolution. Aircraft will still matter, but primarily as interfaces between humans and complex systems. The pilot of the future may spend less time flying in the traditional sense and more time managing information, coordinating assets, and making strategic choices in compressed timelines. This does not diminish the skill or importance of pilots. It elevates their role. They become not just operators of aircraft, but managers of complexity. In this context, stealth, sensors, networking, and decision speed are not ends in themselves. They are tools that enable adaptability, the ability to respond effectively when assumptions are challenged. That is the true takeaway from this comparison. The F-35 and the Su-57 are impressive achievements, but their greatest significance lies in what they reveal about the direction of air power. They show us a world where advantage is increasingly temporary, where systems must evolve continuously, and where understanding matters as much as performance. As viewers and analysts, recognizing this helps us move beyond surface-level debates and appreciate the deeper forces shaping modern military technology. Air combat in the 21st century is not about dominance in the sky alone. It is about navigating complexity, managing uncertainty, and making informed decisions faster than others can. And in that environment, the aircraft that matters most may not be the one that looks the most powerful, but the one that helps its operators adapt when the future refuses to follow the script. As we've seen, modern air power isn't defined by single aircraft, but by how systems, information, and decisions come together. Understanding these technologies helps us better understand how nations think about security, deterrence, and innovation in the modern world. If you found this analysis valuable, consider supporting the channel by liking the video and subscribing for more in-depth, documentary-style breakdowns of military technology and history. Your support helps keep this content educational, neutral, and ad-friendly. Thank you for watching, and I'll see you in the next one.